part of the journal track of the conference, and about single and dual arm motion planning with heuristic search, work by Benjamin Cohen, Sachin, Chitta, Maxim, Likhachev from
a lot of places. Hi, my name is Ben, and I'm here presenting single and dual arm motion planning with heuristic search. And I worked on this with Sachin Chitta. He used to be at Willow Garage, now he's at SRI, and my advisor, Max Likhachev at CMU. So the goal of our research is to create a motion planner that's capable of planning paths for an arm to safely move the end effector from some point A to some point B. Okay, and those points are X, Y, Z roll pitch yaw coordinates. And now we're really motivated from the home tasks, the tasks at home, the cleaning tasks, where we want this robot in our homes, and obviously we want it to plan fast. That's a must. And also, we want it to be able to deal with the clutter that is naturally found in our homes. Also, we're also motivated by the factory automation scenario, okay? And we also need it to plan fast for those situations like this. But also, in this scenario, we need efficient paths, okay? We need paths with short path lengths that will execute quickly so that we could do a lot of manufacturing. And in both of those cases, humans will be working nearby the robot or living nearby the robot, okay? And we want the humans to feel safe. So we need the robot to perform predictable actions. So the robots shouldn't be waving their arms around, making the human feel like they can't walk within its vicinity. So we want the solutions that our planner generates to be consistent, okay? Meaning given similar input, you should expect similar output. So these are the three things we're looking for here in a motion planner. So the bulk of the related work here in path planning for robot arms is sampling based. Obviously, PRMs, RRTs, RRT star, they've been shown to be able to handle very complex motion planning problems very quickly. They're very impressive. But since they don't offer any explicit cost minimization except for RRT star, and they rely heavily on randomization, you don't get that consistency, and you can get wacky-looking motions. Chomp is a form of trajectory optimization that does give you explicit cost minimization. The paths look pretty good, but at times they rely heavily on randomization to get around deep local minima, to give you good feasible paths. So you don't actually get the consistency from there. And our approach is a heuristic search-based approach that we'll be talking about. It gives you completeness, a suboptimality bound, consistency, and your explicit cost minimization, all the things you get with weighted A-star, except the high dimensionality of the path planning for robot arms problem really affects us more than affects them, and that's what we're going to be talking about, how we deal with that. So our approach has these three critical components. We'll go into that right now. So the graph representation. So we made this thing we call manipulation lattice graph representation. Okay, a lattice is a discretization of the configuration space into a set of states, and now each one of our states represents a joint configuration of the robot arm. So here on the right, you see the robot arm of the PR2. It's got 7 joints on it. So each state represents, for the PR2, 7 joint positions. And these states are connected by edges that correspond to motion primitives, which are kinematically feasible motions that could be performed from any given state. And we have 2 kinds of those. We have static motion primitives, which are just your general predefined set of motion primitives, like these, panning the shoulder, flexing the elbow. These are represented by a vector of offsets that can be applied to the joint positions of a given state. And we also have adaptive motion primitives. And these motion primitives are motion primitives that are generated at runtime on the fly using analytical solvers and inverse kinematics to compute the motion required to go from your current state to that goal state in a single motion. Okay? And after we compute that motion, we check if it's valid, if it's collision-free, and then we compute its cost, and we throw it in our graph, just like any other motion, any other edge. So now, this snap to the goal motion that the adaptive motion primitive is, we only do it when we're close to the goal. And this provides us with 2 benefits, okay? The first one is that, when we're close to the goal, instead of searching around for a path to that goal state, we could just use an analytical solver to just generate that path, one single motion, add that edge to the graph. And the second benefit is that in manipulation, you're given a grass pose that you're planning for. You pick up this bottle. You need that gripper to be at this precise grass pose. And now, instead of increasing the resolution of the graph for the entire high-dimensional state space, we could just use this adaptive motion primitive to achieve this exact goal state, this exact joint configuration that we want for the arm, just when it's really necessary at the goal pose. We don't really need it anywhere else. So an interesting thing about manipulation that we found is that when you're far from the goal, when the arm is far from the goal, there's generally not as many obstacles as as the goal region. We're generally trying to, when we pick up this bottle, the robot's arms will start at its side usually, or at a factory, it'll start at this safe configuration. And so for most of the search, you really don't have to deal with a lot of complexity in the environment like you do in the goal region. Okay? And on a robot arm, you actually only have a subset of all the joints that actually move the end effector in XYZ. So we found that we could actually search in a lower dimensional space for much of the search until we get to that goal region, where we need to use, we want to be able to use all the joints in that region to be able to search around for a path. So actually, in the case of PR2 again, here, the robot's gripper is above the dishwasher. It wants to bring it to the sink. This far from the goal, we actually plan in 4D, okay? And closer to the goal, we plan in the full 7D, giving us this multi-dimensional state space. And in the same vein, we use non-uniform resolution motion primitives. Far from the goal, let's use larger motions, hustle to that goal region, and then let's use small motion primitives to precisely navigate through that cluttered region. All right, so to search the graph that we just described, we could use any graph search, but we're going to use an anytime variant of Astar called AAAI. It works by initially generating a quickly but possibly highly suboptimal initial solution, and then keep improving that path as time permits and improve it efficiently. It guarantees completeness with respect to the motion primitive-based graph that we just described. And you get all the standard guarantees that you get with weighted A*, and it really, just like weighted A*, really depends on an extremely informative heuristic. We're pushing in all of our chips on the heuristic here to get us a quick solution. So to guide our search, we need to be able to capture the key complexities of this manipulation problem, and we found that it's the obstacles. Guiding that search around the obstacles in the environment will give us a solution much quicker. So we use the 3D distance of the end effector from the current state to the goal. And normally in motion planning, you use the Euclidean distance. It's a common thing to do. But we use the 3D distance of the end effector, accounting for obstacles along the way. And it's implemented by using a 3D BFS. Okay? And we found that this is dramatically better than using the Euclidean distance. It's also fast to compute. So I'll show you an example here. Here we have a table. You can imagine the robot is in front of the table. That's its gripper above the table. The robot wants to plan a path to that pink sphere below the table. The heuristic is saying, given a Euclidean distance heuristic, saying drive that end effector, drive that search through the table. And down below, in green, you see all the expansions that are required to compute a path. And each green dot represents an XYZ coordinate of the end effector pose at a given state. And here we're using a very high epsilon, an epsilon of 100, to show you if we were to trust this heuristic all the way, this is what would be required to compute a path. Now, the BFS heuristic that we just described would say go around the table. And with the epsilon of 100, these are the states that are required to expand to compute that path. So we found the BFS accounts for obstacles nicely and really helps. All right, so now you know about our motion planner, but it doesn't really work, right? Well, to test the planner, we made these 4 different scenarios. You have a kitchen, a tabletop, an industrial setting. It's for bin picking, and a narrow passageway through a wall. So we compared our planner to RRT Connect and RT Star, and we have a lot of numbers here. RT Connect is the fastest, no question. But we do have sub-second planning times across the board in all of our trials. And our speed is comparable to RT Star, and our solutions have, on average, much shorter length than both the other planners. And RT Star and AAA Star could benefit. They can improve the path as time permits. So we gave them each 60 seconds and said, let's see what you could do. Our planner planned paths that are between 15 and 70% shorter than RT Star across the board on all the tests. There are a lot more numbers in the paper if you like numbers. Here is a video of the robot it planned a path for this hockey stick to go through this window. This window is like 4 or 5 centimeters wider than the hockey stick is long. It's a pretty constrained problem. I am short on time. I'll be showing the videos in the poster session, so you can see it then. Now, we do have dual arm performance results in the journal paper, and I'll also show them in the poster session. But here is just a video of a path that we planned from one side of this wall to the other through this narrow passageway. There's Cheerios in the glass on the tray. It's just showing you that it's not attached. We didn't cheat here. Also, we couldn't use liquid because near the robot. All right, so I just showed you that we're comparable in terms of speed, okay, and our path lengths are pretty good. They're better than the alternates. So let's talk about consistency. So to show you that we get similar output given similar input, we give the robot the planner, same start position, 27 similar but not the same goal poses, and under the table, and we found that we have a much lower standard deviation in path length than the other 2 approaches, RT Connect and RT Star. So basically, with this approach, you get more for your money. Forget about just looking for feasibility now in manipulation planning. That's how it's been for so long. Okay? Now we can also get cost minimization and consistency with comparable planning times to sampling-based approaches. Here is the path length of the risk takes in those trials, just to show you that they're very similar across 27 trials. They just diverge at the end to go to their unique goal poses. And some more consistency results here. Different start positions going to the same goal. To the eye, they're very similar. And all the goals are within this 10 centimeter cube. So in conclusion, to achieve our goals, we use these 3 components, the manipulation lattice graph, AAA Star, and the 3D BFS. We actually do have comparable performance to sampling-based approaches in terms of time, shorter path lengths across the board. Our results show that our planner demonstrates strong consistency for similar input. And our future work is to compare the path costs found in practice using a high epsilon versus the optimal path costs, just to see what we're missing out on here by using a high epsilon. Also, we want to explore other graph searches, and we want to see the benefit of all the different components of our approach. And thank you.
It's really impressive how good these things do work. I was just wondering, this A-star algorithm is already around for some time, and so what do you think is the big contribution applying the different heuristic, applying the different resolution, or making it happen in practice?
We think it's a heuristic, that BFS. It takes about 100 to 150 milliseconds to run, and it's got to run obviously for each start goal pair, and it gives us the biggest benefit out of all the different parts made up the manipulation lattice graph and the other parts. We think we could use another search, without heuristic.
So I was curious to know if you have to. I mean, it's possible that when you plan in a lower dimensional space, that you'll actually get to the point where you're not able to complete the plan. So how much backtracking do you have to do?
Well, in our experiments, we haven't seen it. But I guess it is possible. And
Possibly you'll move the base to be a certain position, and then from there you cannot access the point you're trying to get to. So you'll have to, your plan is going to have to backtrack.
did you say move the base?
Yeah, for example, if you had a mobile base.
Well, we're not planning for the base here. I thought you meant backtrack, from the 70 to the 40. Is that what you meant?
Well, so even if you didn't have a mobile base, it's quite conceivable that you'll have an outpost from which you cannot, let's say, move the tray through an arrow opening. So it might be that, for example, using that particular outpost, you cannot execute. So that's what I mean by the backtracking, the planning, so that you'll have to then, in your low dimensional space, plan a different plan so that then you can get it to an arrow.
Yeah, it's definitely possible. And obviously, we're only complete with respect to the graph that we're constructing here and those motion primitives. So it's possible that it wouldn't be able to do it at all, given that we're using a smaller, lower dimensional state space in the beginning. But we haven't seen a lot of backtracking out of that goal region out and then enter it with a different approach. We haven't seen that much, but we can.
Right. So you have backtracking in there, you just haven't seen it happen.
Yeah.
I was wondering if there's, in the smaller dimensional space, if you have concerns about collision detection, is it possible that you have taken such large steps that you are planning through objects that exist in the world?
We're interpolating along that motion, collision checking along the way, like literally every 2 or 3 degrees in joint space of the arm.
You still do that at a finer resolution?
Yeah, and it's expensive.